Thank you so much for the introduction. And also I want to thank the organizer for this amazing workshop. I have a very, I learned a lot from the past 2 days, and I really hope that this workshop could, last for a little bit longer, but today is the last day, and I will really, enjoy my time here, and hope like next time we can reunion at some point. So today my talk it could be regarded as some short, cute applications of optimal transport in some mass finance topic in the risk measure. And this is a joint work with Ray from UT Austin and Jing Chen, who is my colleague at Johns Hopkins. So we want to mention that risk measure itself is actually a very well-studied topic in mass finance, but we want to emphasize that in the data-driven scenario may have some new challenges. So in the first few of my slides, I will briefly talk about the risk measure to make sure everyone in the audience stay in the same page. And then I will talk about how should we make use of the optimal transport to handle this new challenge by the data. So risk measure, basically it's functional. So give me any financial loss X, which is a random variable, and then I will map it to some real numbers. So basically a client come to me, and then I will tell them that how their portfolio look like by giving them some risks, right? So by evaluate their risk and then give them some idea how much money they are going to lose in the future. So then to well define this risk measure, we usually start with the state of the states, the omega, and usually we have infinite many of the states. So omega is chosen to be the measurable space, usually filtered, and also often with a reference measure, we use this P here. So then as I just introduced, the risk measure maps this X to a real number, basically give you the idea how much money you are going to lose. So then in the multi-period setting, we can similarly define the following dynamic risk version. So that means that if I have this portfolio that will last for capital T time, then at each of the day during this period, I'm going to tell you using this little rho T that how much money you're going to lose at capital T within every single day between this period, right? So then from the literature, luckily we find that it's equivalent to say that I do this risk evaluation. It's equivalent to think about what would be the worst case scenario that among all the probability space, and then I give you the loss you are going to, the money you are going to lose under this worst case scenario. The corresponding number will give you the risk measure, right? So and then we have this convex risk measure could be written into this following form. So as you can see, we actually evaluate the worst case scenario among uncertainty set M, which is usually a convex subset on the probability measure omega. And then together with alpha Q, we call it the penalty function that marries the deviation of this Q, this worst case scenario, from this reference measure P. So, and also to help simplify the risk evaluation, we usually consider this following two very important property of the risk measure. The first one is what we call the low invariance. So basically the high level idea is that if I can have this X and Y have the same distribution, then same low here induced by the P, then I should have the same risk evaluation on both of them. And then in the dynamic version, to help us to simplify the evaluation at each stage, we hope this risk measure has the following time consistency. That means that if I want to evaluate the risk through the whole process, X1 goes to X capital T. Now in my paper, we consider the discrete time setup. Then we should be able to decompose it into this following way. That is, I can enable to tell you that at each of the day, how my risk should be look like. So then a classic example to give you is what we call the entropic risk measure. Basically, that means that we choose this alpha Q to be the KL divergence between Q and P, and with lambda to be the risk averse preference of the decision maker. Then given different value of the lambda, we should be calculate the corresponding rho x here, right? So this is just so far what have well studied in the literature. And also there's a very important, result saying that if for any low invariant time consistent convex, which is the three very important property we mentioned briefly in my previous slides, for this risk measure, we could always write it into the form as some entropic risk measure. So basically, it's equivalent to write it to construct an uncertainty ball, this M1, and then together with KL divergence and write it into this way. To show the time consistency, we can by setting this rho t, given the information up to the time t, then we can decompose it into this following way, right? So far so good. It seems that we have a very neat and a clear structure for the risk measure we want to study. So why am I here? Is that we realize that if we want to apply it, so mathematically speaking, everything so far is very neat and very clear. However, let's think about how should we apply it in practice. So the first one we want to mention is that why we have to use this low invariance. Because in theory, people usually say that this omega, which is the state of the world, is typically very abstract. And what we can observe, what we can evaluate from the data is the payoff distributions. In theory, we want this reference measure P chosen to be something that could encode every relevant risk information. So mathematically speaking, it has to be something that every distribution on this space should be absolute continuous with, right? And also such a P could be very abstract. However, with this low invariance property, it actually helps us to simplify the risk measuring process by focus only on the low instead of the specific realizations. So in theory, it gave us a very clear result. However, what we have in practice are the realizations, are the data you can observe from the past stock market or your portfolio behavior, right? So in practice, people may think about, it seems to us that it's very natural to replace such a reference measure with the empirical one you can directly get from your data, from the simulation you got from some scenario tree-based computational method. So, however, it may be an issue to choose such an empirical measure in this framework, because that means that from the decision theoretically, it may not be able to capture all the source of uncertainty, and mathematically speaking, the empirical risk measure, the support may not be the entire space. So basically, this restriction will apply to all scenario tree-based computational method. So that will be an issue. Due to this mismatch between the theory and the practice, we hope to draw this low invariance requirement and allow us to consider the scenario that has never been seen before in your data. So that's our motivation. But before we go to our construction, let's take a closer look why this low invariance with empirical measure will be an issue here. So to see that, let's focus on the single period for now. So then for our reference measure chosen to be the empirical one, the normal one. So as you can see, it could be written as a PI, which is the likelihood of assigned in each of the realization cosine hat I that I have observed before in my data. So if using what theory tells us that we simply just replace this penalty function alpha to be the KL divergence between Q and P, then the corresponding Q that we consider in this scenario will only penalize on the deviation of the likelihood between QI and PI, right? So basically, the corresponding Q we consider here, it fixes the realization at cosine hat I, right? But only change the weight or the likelihood we assign in each of the data points, right? So then you can see that that will be an issue because if some unseen scenario happens now and I want to evaluate the corresponding risk, then like from the audience, you may think about, well, if you say that KL divergence doesn't work in this scenario, then it's very natural to introduce some optimal transport-based distance to allow the perturbation from the realization in the past, this cosine hat, to some scene like a scenario here. So for example, if we consider to replace this alpha Q to be the Wasserstein distance, right, between the Q and the P here, indeed, this penalized on the deviation of the states, allow us to perturbate from the previous observation cosine hat to the new cosine Q here. However, as also quoted in Jose's talk, in this scenario, the corresponding Q we consider actually the worst case states are defined through this moral envelope. Basically, the idea is that if previously I observe endpoints, and then my new Q considered in this scenario, the worst case one, so the state will be perturbed into another one with at most one point will split into two situations. But the weight or the mass we assign on each of the states are the same, right? So in that case, if we only replace the penalty term with the Wasserstein Q, Wasserstein distance, then we actually also didn't allow us to change both of the likelihood and also the deviation from the different states. So then what if we want to combine them together to see whether we can make the framework make more sense? So that means that if we allow for both of the deviation of the likelihood and also the states, possibly it's very natural to consider to define the penalty function as the inf convolution of your Wasserstein and KL divergence. People sometimes call it the gamma divergence in the literature. So basically, if we choose our alpha Q to be the mean between the Wasserstein and the KL divergence, then immediately we can show that the corresponding worst case scenario Q considered in this robust representation indeed has this following form that could be decomposed as the deviation from the states and also the deviation of the likelihoods, right? So here we can just define it through the most general one, like with a distance like the norm defined in this transport cost, and then the corresponding Wasserstein could be used in here. No, like specifically, we just use this little t to represent the transport cost that we consider in the Wasserstein distance. Yeah, D has to satisfy the triangle inequality. Yes, that's a Wasserstein one. Yes, indeed. Yeah. Yes. Yes, P is given from the empirical, the normal measure. Sorry, could you? Yes. How you can avoid fixing the with that so here, so this part represents, so as a comment before, this D represents the deviation, like the norm I consider, the metrics I consider in the Wasserstein distance, which is penalized on the deviation from the cosine hat, which is observed in data, to some new possible like states, which I denoted here as the cosine Q here. So that's why I note here that as the deviation of the states. And then in the second part, the QI represents a new likelihood I'm going to assign to different data points, and then using this penalty as this to define different likelihoods on the different states here. So in other words, the order was like P theta in KL, then maybe now. Yes, so P is something we observe from the data, the nominal one we choose. And then basically the high level idea is that we first use K out to change the likelihood, and then use the Wasserstein one to perturbate to the new states. Okay, so then similarly as what we have in the entropic one, we can rewrite the resulting risk measure into this following log exponential part, with here, again, this D represents the metrics I use in the Wasserstein one, and the lambda represents the different risk aversion preference in the risk measure here. So this is a single case scenario, so single period scenario. So how about we want to extend it to the multi-period scenario? Then in that case, we may think about how to perturbate the data like more wisely, because in the multi-period process, if I use my cosine t here, then we must respect the temporal flow of the information. That means that at each of the little t, the decision should only depend on given the information available up to little t here. Then if we just replace the Wasserstein on the Wasserstein distance for this process here, it may violate such a causality because it could transport the feature information backward to the current decision time t here, right? So given the previous, the materials has already, gave you some idea how should we deal with this causality that leads to the causal transport distance. So the high level idea is that if we want to restrict our coupling gamma to satisfy this following causality, the corresponding transport distance we define as this process is what we call the causal transport distance. So in that case, we can show that this alpha q, instead of using the Wasserstein one, we should replace it with a causal one, enable us to allow the perturbation maintain the causality in the time like series data, right? So then given that, we are able to show, so seems to us that so far so good. If from us as a data-driven scenario, we introduce the actual Wasserstein or the causal distance to help us to perturbate to the unseen scenario. And however, we also find that it's not the only issue we meet when we try to replace it. The other issue, like if we only use the normal one we got from the data, is what we call the mismatch of the filtration. Because if you think about, if I want to define the conditional risk mapping at each of the period little t, I need to filter using the filtration like up to the time little t here. However, the normal process, this cosine hat, generates a corresponding filtration. We call it the filtration hat, the filtration hat. Then the filtration of the possible all the outcome should be typically a more finer, right? A more finer filtration here. So conditioning with respect to this normal filtration f hat is not rich enough to help us to well define such the corresponding dynamic risk measure, right? So that's another issue. So how should we deal with it? Well, the idea is that from the mathematical way, we should make sure that this filtration track both of the real path cosine and the normal one cosine hat at the same time. And then we consider the product filtration defined together with the filtration t and the filtration hat. Then we should allow this new definition of the dynamic risk measure on this GT measurable function, this ZT here, right? So in that case, that means that if conditional on each of the period risk, we should consider how to define the risk with respect to this zeta t plus 1, which track both of the both of the real one, that the perturbator process, and also the normal one we observed from the data. And then we should define the conditional risk mapping, not only just conditional on the filtration hat, but also on the past observation of both of the zeta from T1 to T minus 1 here. And then this conditional one is depending on the ZT, which is the random variable on the product space. In that case, given the very good property of the causal transport distance and also the KL divergence, we can again showing that our corresponding dynamic risk measure could again decompose it using the conditional risk mapping we defined before into this like a decomposable way. As you can notice that here our X represents the random variable defined on the psi capital T here. And then in each of the stage, we should evaluate on the product space of both the perturbate one and also the past observation one, the normal psi hat one. And then in this case, it may not be highlighted in my slides, but we actually define a new version of the dynamic risk measure. So in this sense, we are going to show that it is indeed a time consistent dynamic risk measure in the sense of that for any x1 and x2, if we have this inequality, then for the earlier time little s, this inequality should also maintain, right? So to summarize what we have so far is that we are actually define the corresponding dynamic risk measure, and if we denote it into this log exponential way, we can show that for every GT variable ZT, we can compute this rho T, this conditional risk mapping of each of this ZT only depending on the psi hat here, which is the data-driven like method to calculate the corresponding conditional risk mapping, and then we can use it in data, and then to make sure everything here is well defined, right? So a quick takeaway for today's talk that is that we are able to show a new definition of the time consistency, and in that case we define a multi-period risk measure with respect to the normal low p hat, which is not low invariant because it allows the measures beyond the absolute continuous, and also it allows the deviation of both the states and the likelihoods. And to make sure this risk measure is well defined, it should be defined on the product space and also the product filtration. So our paper will be posted online soon. If you are interested to take a closer look at the details, I'm happy to share through the email about the draft. Thank you so much.